Suppose I start bicycling down the highway around mile marker 17. You know how highways have those mile marker signs? At 6 a.m. Later at 8 a.m., I take a break at mile marker 47. What was my average velocity? So average velocity is going to be my position at the end minus my position at the start divided by the end time minus the start time. So we are talking about time between some start time and end time, and the function that tells me the position as a function of time. Well, then P of B is my position at the end, which is 47. P of A was my position at the start, which is 17. B, the end time, was 8 a.m. And A, the start time, was 6. So 47 minus 17 is 30, 8 minus 6 is 2, and this gives me an average velocity of 15 miles per hour. So who knows what happened in between? Maybe there were times when I was bicycling really slowly at like 5 or 10 miles an hour to take a little break. Maybe there were times where I was sprinting at 20 to 25 miles an hour to get a little extra work in. But on average, for those 2 hours, I must have been traveling an average of 15 miles per hour. So I can make it 30 miles in 2 hours. So we've done that before, but I wanted to remind you that this is the average rate of change formula. So you're kind of generalizing this away from just the position function to any function. And we say the average rate of a change of a function f over the interval from a to b is given by this formula. And before we move on, just want to make sure, does that connect in your head, the ideas here? Because the velocity is like the rate of change of position. But more than just position, you have rates of change. So as I'm biking down the road, if I actually want to know my instantaneous velocity, what I could do is I could buy one of these little devices where you just clip a magnet to one of the spokes of your bicycle wheel, and then along the fork you attach a little sensor, and the only thing that this sensor does is it looks for the magnet. And when the magnet comes across the sensor, gets near the sensor, it induces a little electrical pulse, like just a current goes, and then it clocks it. It determines what time each pulse happens. And if I have this device, and it's telling me when the magnet passes by the sensor, it would tell me how much time has elapsed during one rotation of the bicycle wheel. If you know how much time has elapsed in order to make your wheel rotate one time, how could you calculate the speed you're traveling? Yeah, how big the wheel is. The area of the wheel?
No.
What's the word? It starts with a C.
Oh, circumference.
Circumference. Yeah. If I know how much time has elapsed, call it like delta t, how do I calculate the speed of the bike? Where I would take the circumference of the wheel divided by the amount of time it takes for the wheel to make one rotation. So you get distance over time. You could measure the circumference in miles, and it would be a tiny fraction of a mile. And then you could measure the delta t in hours, and it would be a tiny fraction of an hour, and you can make it miles per hour. Um, and so for my practical purposes, that is the instantaneous velocity. The wheel is passing, a full rotation so quickly whenever I'm on the highway riding my bike that I don't really care to have any finer resolution in my velocity, right? Like it's practically as close as it needs to be to in the instantaneous velocity of my bike. But in reality, we're just doing kind of the average rate of change formula, right? Like we're just taking the position at the end, 1 rotation, minus the position at the start, 0 rotations, and dividing by the amount of time that it has to take to make that 1 rotation. So really, this is just an average rate of change, like average velocity, over a tiny interval. This kind of instantaneous velocity is really just the average velocity over just a really, 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 really small time interval. And so when we say the derivative is the instantaneous rate of change, that means I could write the derivative of a function f as being the average rate of change of this function. So I'm going to write the average rate of change formula. But I specifically want a really, really tiny interval. I want B and A, the endpoints, or the start point and the end point, I want those to be really, really close to each other. So now that we know about limits, I could think to myself, what's the limit as B approaches A of the average rate of change? In other words, as I let B get closer and closer to A so that the interval becomes smaller and smaller and smaller and smaller and smaller, what is this average rate of change approaching? So in exercise 2 on your homework, I'll show you exactly what I want for the solution. Exercise 2 says, beginning with the average rate of change formula, develop the formal definition of the derivative carefully, logically, step by step. So, right here, we have the average rate of change formula. With, you can imagine a tiny interval from A to B. I should use square brackets. What I'm going to do next is say, define this. H is going to be the width or the duration of the interval. So H is going to be B minus A. Then, when B is approaching A, that means H is approaching 0. And if I want to take this equation, h equals b minus a, and rearrange this to solve for b, b would be equal to a plus h. Okay. So revisit my green formula. And so, okay, this derivative of the function is going to be the limit as h approaches 0 of f of a plus h minus f of a divided by a plus h minus a. Then, assuming here we want the derivative of f at the point x, what we should do is rewrite this green formula. So I got f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Because in the denominator, I've got a plus h minus a, so the a's cancel, I just get an h. And the only thing I did in the numerator is I just changed the a's to x's, because normally when we write the derivative, we are talking about a point x. And so whereas a was the starting point of some interval, well, we're letting the duration of the interval, or the length of the interval, approach 0. And so the interval itself is shrinking down to the point, and so we'll just call that point x. And so we get the limit as h approaches 0 of f of x plus h minus f of x divided by h. This is called the formal definition of the derivative. It's a really important one to know. So on exercise 2 on your homework, this could be a really good test question. I might put this on your test. Is say, beginning with the average rate of change formula, develop the formal definition of the derivative. You don't have to write exactly what I wrote word for word, but you have to represent the same ideas. Right? On a test question, you would have to show me that you know what I'm talking about here. You have to write enough so I have enough evidence to understand that you understand how you get from this average rate of change formula, where you want the interval to shrink, all the way down to this formula that we're going to use as the definition of the derivative.
Do you want us to write out the steps to it, or if we just showed the 3 different formulas, would that be okay?
I would want you to show at a minimum this, and this in green. Plus, I would also want you to say define h equals b minus a, so I know where the h comes from. And when b approaches a, that means h approaches 0. B equals a plus h. Include some of these details again, just so that I know that you understand this argument. Okay. Are we good? Do you need more time? Okay. So here we go. Exercise 3. Using the formal definition of the derivative, prove that the derivative of x squared is equal to 2x. So obviously, I'm not asking you to use the derivative power rule, right? If you get this question on the next test, on test number 4, don't just say derivative power rule and move on, right? That's not what we're going for. What I'm trying to show you now is like, how do we know the derivative power rule works for x squared? Right? Who came up with the derivative power rule? How did they come up with it? Why are they so convinced that it works? Okay. So this derivative, the derivative of x squared, is going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h, where f of x is x squared. So what is f of x plus h in this case?
F of x squared plus h.
So I'm taking the f function, which is the x squared function, but I'm replacing the entire argument with x plus h instead. There you go. Yeah, so everywhere I see an x, I'm going to replace the x with x plus h in parentheses. That's really important that you know what this means, because every single time we use this formula, you'll need to replace x with x plus h in the original function. In this case, x plus h all squared. And then I get the limit as h approaches 0 of x plus h squared minus x squared divided by h. So, if I try to directly evaluate this limit and just plug in h equals 0, what happens?
H squared.
I'd get x plus 0 squared, which is just x squared. X squared minus x squared is 0. H is approaching 0. I get 0 over 0. It's like undefined, right? So I can't do that. What I need to do instead is go ahead and expand the numerator. And in the numerator, when I expand this, it's going to be x squared plus 2hx plus h squared minus x squared over h. How do I simplify that? The x squareds cancel.
And you can take the h out of all of them, right?
Nice. Yes, I can divide everything in the numerator by h. what's the limit as h approaches 0 of 2x plus h? 2x. So we didn't use the derivative power rule. And that's important because what we're trying to show is how do you actually prove that this derivative works? If we just say, oh, well, it's a rule I memorized, it's not a good explanation. It's like, you know, when you're a little 5-year-old kid and you ask your dad, why is the sky blue? And your dad says, yeah, because it is. It's like not a very satisfying answer. And so mathematicians are always about proof. We're always like, you know, you think this is true, but prove it. Well, this is the logical proof. Why we say the derivative of x squared is 2x? Because we have a formal definition of the derivative. And when I use the formal definition of the derivative, I can plug it in and it works. Do you understand how to do exercise 3? All right. Exercise 4. Using the formal definition of the derivative, prove that the derivative of mx plus b is equal to m. So, you know, like y equals mx plus b is a line. M is the slope. So this is an interesting question because it's saying, you know, prove that the derivative of a line is the slope of the line. And to do this, we're going to say f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. And f of x is mx plus b. F of x plus h is
M times x plus h. Speak.
Yep, m times parentheses x plus h plus b.
So for the x plus h, so we just plug x, the f of x, we just plug that function wherever x is, and then x plus h.
Exactly.
Okay.
All right, so then let's rewrite my limit. All right, m times x plus h plus b minus mx plus b over h. And if I just tried to plug in h equals 0 at this point, it's going to give me 0 over 0, so yuck. Can't do that. Instead, I need to take the limit as h approaches 0 and just simplify the numerator. Just kind of expand everything out. How does the numerator simplify?
M.
The mx is canceled.
And the b's cancel.
The b's cancel.
And then the h's will cancel else, which just leaves you with just n.
Yep. So, you know, you can probably see where this is going. I mean, obviously you can see where this is going, you know. In these types of problems, even on the test, I'm going to give you the answer, right? That the derivative is m. So you know when you're done with your proof, you have to get this. And if you don't get m, then you did the proof wrong. And you've got to, you know, check it.
Okay, so
Go back and find your mistake.
Okay, so then we just have to work.
You'll know if you get the answer right or wrong.
All the like the like proofs, will they all kind of follow the same process of like you plug it in and then you expand it and then everything will kind of cancel to your answer?
Yes. It's always a matter of writing the formal definition of the derivative, plugging everything in, and trying to algebraically rearrange this, simplify it until everything cancels. Okay, questions? Nope. So that makes us, you know, a little bit more comfortable saying that, like, the derivative is like the slope of a function, because if I plug in a linear function, then it's the slope of a line. Using the formal definition of the derivative, prove that blah. So this is exercise 5. This time we'll write down the formal definition of the derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And here, my function, where I'm taking a derivative, is 1 over x. And so f of x plus h is going to be what?
1 over x plus h.
Yeah. 1 over, and then x plus h is all in the denominator where the x was. So, no surprises. We just plug that in. Obviously, we can't just plug in h equals 0. If we do, we get 0 over 0. It's not good. So what do I do instead?
Expand out. I like the common denominator.
There you go. Everybody's got it. I need to find a common denominator. In finding a common denominator, I mean, hopefully you guys know how this works. We've only been doing it since like 7th grade or whatever. But if I'm trying to subtract these two fractions, like 1 over x plus h minus 1 over x, then I find a common denominator by multiplying the first fraction by what? Yeah, x over x, and I multiply the second fraction by x plus h over x plus h. And so the common denominator then between these two is going to be x times x plus h. And then what I'm going to get is x minus h. Or x minus x plus h, if you want to write it like that. And then I still have an h in the denominator. Bring this around, and we start over here. In the numerator, x minus x, the x's cancel, minus h, don't forget that's a negative, so I get minus h over x squared plus hx. That fraction divided by h. So when I learned how to multiply fractions, our teacher told us dividing is the same thing as multiplying by the reciprocal. Dividing is the same as multiplying by the reciprocal. The reciprocal of h is 1 over h. And that helps me see a little bit more easily that these h's are going to cancel and multiply fractions across the top, across the bottom. So this is going to give me the limit as h approaches 0 of negative 1 over x squared plus hx. Now, can I take the limit as h approaches 0? Yeah, what's the limit?
1 over, negative 1 over x squared.
Well, that's a relief because that's what I'm supposed to prove. That is negative 1 over x squared. So perfect. We know we did it right. But to get full credit for this test question, I've got to see your work. I've got to see every step of your work so I know that you know how to do it. I'm already giving you the answer, so you can't just write the answer. Okay, any questions about this one? All right, a few more of these. Using the formal definition of the derivative, prove that. Okay, so I'm going to change colors. I've been using a lot of purple today. Let's use some more green. Maybe blue. I don't use blue quite enough. Blue's been a little bit underappreciated. So if I say f of x is the square root of x, then f of x plus h is what? That's it.
When we get 0 over 0 in this case, what would happen if we applied L'Hopital's rule?
So, good question. I like the question. All right, so 0 over 0 would be an indeterminate form. And what you would do is you would take L'Hopital's rule, but you would take the derivative with respect to h, not with respect to x, because my limit variable is h. And so this time you take the derivative of top and the derivative of bottom with respect to h. And so you would work it out and you would get the right answer. You will get the right answer if you use L'Hopital's rule and you take derivatives with respect to h. But I specifically don't want you to do that this time for this test. I don't want you to use L'Hopital's rule because what we're trying to do in this last unit is demonstrate how calculus was invented, right? In the 1600s, smart people across Europe all sat down at their desks and together worked as a group to invent calculus. And the important learning objective is to say, hey, I actually understand like what the foundations of calculus are and how this came about. And L'Hopital's rule is maybe something we'll prove at the very end of the semester if we have time. There's a lot of other things we want to get to. But for right now, let's just pretend we don't know about L'Hopital's rule. And that we want to sort of engage in some math history here and do it the way that the first Isaac Newton and Leibniz and all those old folks from hundreds of years ago would have done it. But that's a great question. All right. So what do I do here? How do I subtract these square roots? It's okay if you haven't seen this before. I don't think I had seen this before until I took my Calculus 1 class. It's a little bit obscure, the trick here. But this is going to be x plus h minus square root of x, like that, divided by h. And then what I'm going to do to make this workable is I'm going to multiply by the square root of x plus h plus x, square root of x. And I'm going to multiply by that on the top and the bottom of this fraction. So it's like multiplying by 1. I'm not changing the value of this limit when I multiply by 1. But this is actually going to allow this thing to work out once I finish doing all my multiplication. Like in the bottom of this limit, in the denominator, we're going to have h times square root of x plus h plus h times square root of x. In the numerator, I'm going to be a little bit more careful about how I multiply in the numerator, because you've got to kind of FOIL this. Because in the numerator we've got square root of x plus h minus square root of x, square root of x plus h plus square root of x. So this is going to be x plus h, right? This is going to be negative square root of x, square root of x plus h. This is going to be positive square root of x, square root of x plus h. And this is going to be negative x. So hopefully you can see that these are going to cancel. And I can't make it not do the crazy vertical thing. Go back and erase all the crazy stuff. Okay, those are going to cancel, the stuff I highlighted in red. So that what I'm left with is x plus h plus negative x. So the x's cancel, and then I just get h. Okay, how do I simplify this limit further?
All the h's cancel, so you get x square root of x plus h plus x.
Yes. The h's cancel. And then when I take the limit as h approaches 0, this is going to be 1 over square root of x plus square root of x. which is 1 over 2 times square root of x. So this is kind of a crazy trick. And occasionally you see this happen in like college algebra classes. But the idea is we're multiplying the top and bottom by what we call the conjugate of this expression. It's a conjugate because these are square roots and these are square roots and this is minus and this is plus. And so I know that with having opposite plus and minus signs, that these terms are going to cancel each other. And then because these are square roots, well, these are not going to have square roots, right? When they multiply each other. And so if my goal here is just get rid of the square roots in the numerator, then multiplying by the conjugate is the safest way to do that. And we got the derivative that we wanted to get. Any questions? Okay. The derivative has the property of additivity. I'm saying this word a lot. But additivity just means if I'm taking the derivative of something that looks like two functions added together, then I could just take the derivatives of those terms separately. So it says, using the formal definition of the derivative, prove that the derivative has the property of additivity. So what this means, and what I want you to do is say, all right, I'm taking the derivative of f of x plus g of x. And that's going to be the limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x plus g of x divided by h. That's what I get if I just plug that expression into the formal definition of the derivative. With a little bit of care, you might see that this is the same thing as f of x plus h minus f of x plus g of x plus h minus g of x divided by h. And, you know, I can break up a fraction where the plus sign is, so this is like f of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h. And limits have a property that says I'm allowed to break up the limit when I'm adding two things that both have limits of their own. And what is this? This is just f prime of x plus g prime of x.
So we'll definitely have a question like this on the test, right?
Yeah, maybe not exactly about additivity, but like there will be at least one, probably two, maybe three questions using the formal definition of the derivative,
Okay.
like your homework questions, for example.
Right.
I'll probably pick 2 or 3 homework questions and put them on the test. And so that might seem a little bit silly that we even have to prove this, but you know, there's lots of operations in math that do not have the property of additivity, like I don't know. It's not that I'm struggling to think of an example. I'm just struggling to think of an example that you've seen already. Because all the good examples come from like upper level math classes. But it's okay. The derivative has the property of homogeneity. And homogeneity means that if I've got a scalar, like a constant multiplier, I can just pull that outside of the derivative and not have to worry about it while I take derivatives. And again, if I wanted to prove this using the formal definition of the derivative, maybe something that I would write down is say like, I want to take the derivative of k f of x. Well, this would be the limit as h approaches 0 of k times f of x plus h minus k f of x divided by h. Which is like k times f of x plus h minus f of x over h. And limits have a particular property where I can just multiply by a constant on the outside, because limits have that, what that property is called. Where if you're multiplying inside a limit, you can just break the limit into separate factors. And so I'm breaking the limit up into separate factors, but the limit of k as h approaches 0 is just k. And so that's, of course, k times f prime of x. So that one's pretty straightforward.